どうも、勝手に電力2.0で始めたいと思います。今日1125回目ということで、スマートエレクトリフィケーションというところを少しIA とか IDNA とか出しているようなところなんですね。市場系を読ませてもらおうかなと思っています。イノベーションランドスケープということで、イノベーション関係のところになっています。イントロダクションな、Systemic innovation is needed to achieve smart electrification of end-use sectors. The world has already begun a historic shift toward cleaner source of energy. Rapid reduction in the cost of solar and wind technology have led to widespread adoption of these technologies, which are now dominating the global market for new power generation capacity. やっぱり太陽光と風力ってとこが、大きくテクノロジーとしては大きいと。But the pace of change must accelerate if we are to meet sustainability and climate goals. We need an even faster expansion of renewables along with a smarter, much more flexible electricity grid. Equally important is the need for significant increases in the range of products and processes that run of green electricity in major end-use sectors, notably industry buildings and transport, because the electrification of the end-use uses enables the use of efficient technologies. Widespread electrification combined with efficiency measures will decrease total global energy consumption. In Irina's analysis, meeting the goal of the 2015 Paris Agreement on climate change will require the share of electricity in the energy mix to rise from 22% in 2020 to 51% in 2050, as shown in the figure final energy mix in 2018 and 2015. 2020 in the まず374エクサジュールってことですね。トータルファイナルエナジーコンサンプションってことで、やっぱりこのフォッシルフューエルズがもう63%あるのが、2050年の1.5度シナリオで言えば、実際全体自体も353エクサジュールになってるんですけど、フォッシルフューエル自体が実は12%に減っていて、一番結構大きいなと思うところはこの51%ですよね。実際このリニアブルシェアインエレクトリシティっていうところが、実際28%が91%になっていたり、ダイレクトエレクトリシティが22%から51%になっている。だからやっぱり電化が進むってことと、リニューアブルが進むってことが、めちゃくちゃ大きいと。But the electrification of end use alone is not enough. Electrification must be done in a smart way, both by interconnecting the power sector with other energy sectors such as heat and mobility, and by enabling flexible source across all energy sectors. なので、ヒート、まさに熱っていうところとモビリティですね。やっぱり電化電動化がめちゃくちゃ必要だと。Electric vehicle, for example, not only cut greenhouse gas emissions dramatically, they can also pay electricity to the grid, reducing the need to build additional generation capacity. Smart electrification through sector coupling, flexibility, and energy efficiency thus prevents a high electricity load for the power system and is a tremendously powerful tool for decarbonizing the energy sector, including end uses. Smart electrification enables the power system to accommodate new loads in a cost-efficient manner. It will also build flexibility into the power system, thereby permitting the integration of the higher share of renewables and making the power system more robust and resilient. Smart electrification is the most cost-effective solution for decarbonizing major end uses such as transport and heating. やっぱり電動化、電化がめちゃくちゃ効率的だっていう話ですね。Moreover, smart electrification with renewable creates a virtuous cycle. Electrification drives new uses and markets for renewables that in turn accelerates the switch to electricity for end uses, creating even more flexibility and driving further growth in the use of renewables and continued technological innovation. Growth and innovation also cut costs and create additional opportunities for investment and business. Innovation is the foundation for smart electrification and the global energy transformation. Most innovations cannot be implemented in isolation, nor are they limited to technology-based solutions. Along with innovation in technology and infrastructure, innovations are also needed in market design and regulation. やっぱり規制とかいろいろ大事です。マーケットデザイン、system planning and operation, and business models. Innovative solutions will be consequently emerge from the complementary series of advances across multiple components of energy systems and leveraging the synergies of these innovations in the process called systemic innovation. And the 100 key innovations identified in this report are spread across 4 dimensions. 1. Technology and infrastructure. 2. Market design and regulation. 3. System planning and operation. And 4. Business models. It is only by matching and leveraging synergies in innovations in all parts of the power system and end-use sectors, and including all relevant actors and stakeholders, that successful solutions can be implemented on the ground. Dimensions of systematic innovation ということで、システミックイノベーションということで、4つの要素を挙げています。まずはこの technology and infrastructure, and market design and regulation, system planning and operation, で、ビジネスモデル。この辺が全部融合しながらうまくイノベーションというのがシステムでやっていくと。Smart electrification cannot be pre-packed. Optimal strategy for power system design and the application of innovation will vary among countries and their specific attributes, including both the technical and economic aspects of a given power system and its social and cultural context. Electricity will be the main energy carrier in future energy systems. Achieving the Paris Agreement goal of limiting the increase in the global average temperature to 1.5 Celsius relative to pre-industrial levels in the unifying principle behind IRENA's 1.5 Celsius scenario. To achieve that scenario, the share of electricity in total final energy consumption will have to grow from 21% in 2019 to 29% by 2030 and to 51% by 2050. This can be achieved through tremendous growth in technologies that operate on electricity, many of which are already available. These include electric vehicles and heat pumps will provide heat for buildings and many industrial processes. In addition, end use that are difficult to electrify directly, such as other industrial processes, can be electrified and decarbonized indirectly with green hydrogen. やっぱりこの実の電化とか電動化しにくい部分っていうところが、グリーンハイドロジェン、グリーン水素ですね。Produced using renewably generated electricity. By 2050, global electricity demand is set to be 3 times what it was in 2020, posing challenges for power systems and raising the importance of energy efficiency. However, given the enormous benefits of electrification and decarbonization, governments around the world should not see rapid, smart electrification as a threat or onerous task, but rather as a golden opportunity to accelerate economic growth, improve energy security, reduce the growing impacts of climate change, and achieve other important sustainability goals. Table 1 summaries the levels of electrification needed to reach the Paris Agreement targets. Electrification progress toward 2050 based on IRENA's 1.5 system scenario. 1.5 のシナリオのための、実際の目標はどうなっていくかということですよね。Share of direct electricity in total final energy consumption ということで、電化のところのダイレクトエナジーということで、エレクトリシティを使うところが、もう51%、約やっぱ半分以上は電気にしていかないといけない。Share of electricity in transport sector。トランスポートセクターはどうしたらいいかってやっぱり半分以上と。Share of electricity in building sector。ビルディングセクターももっとしていかないとですね。73%。Share of electricity in industry。インダストリーがなかなかしづらいので 27% ぐらいなので、しっかりグリーン水素みたいなのを使っていこうと。Electronic and plug-in hybrid like passenger vehicle stocks がもう2000万台ぐらいいってるとですね。Passenger electric cars on the road 実際に2000万台。実際に PHV、プラグインハイブリッドとか、実際にエレクトリック EV とかがもう2000万台。2000ミリオンですね。2000ミリオンなんで、実際には21億とか、21億台とかすごいですね。エレクトリックビークルチャージャーも23億チャージャーとか、めちゃくちゃ出てくるってことですね。で、 Electrification and energy security in Europe. The onset of the crisis in Ukraine in February 2022 triggered a severe energy crisis in Europe. Not only did the price of natural gas from Russia soar, but electricity prices also climbed steeply because of the still high use of gas to generate power. やっぱりガスの影響は実は電気代にも起こると。As a result, European industries which are highly reliant on natural gas are losing competitiveness, and energy bills for European citizens have soared dramatically. This energy crisis is revealing the need for Europe to accelerate its energy transition. In addition to lessen the impacts of climate change, resilient and more secure energy systems will ensure stability, competitiveness, affordability, and sustainability. Integrating high shares of renewables in the power system and using the result clean electricity to fuel end uses will decrease the dependence on gas that helps cause the current crisis. The current energy crisis in Europe may ultimately be an accelerator for the much needed energy transition. やっぱエナジートランジション逆に加速したってことですね。Innovation landscape for smart electrification of end-use sectors. This report presents landscape of innovations to help policymakers formulate smart electrification strategies. As noted, it includes 100 key innovations for both direct and indirect electrification end uses. The innovations were selected based on the analysis of hundreds of real-world projects in consultation with more than 150 external experts from across the world. The report also provides a list of important topics of often overlooked when developing smart electrification strategies. The report is divided into 3 parts corresponding to 3 main power-to-X routes for smart electrification. Power to mobility 3つあるんですね。Power to mobility まずは mobility ですね。Maps 35 key innovations for smart electrification of the transport sector. Power to heat or cooling maps 35 key innovations for smart electrification of the heating and cooling sector across 3 segments: buildings, industry, and district heating and cooling. Power to hydrogen maps 30 key innovations for smart indirect electrification to produce green hydrogen with renewable electricity via electrolysis. This section is limited to green hydrogen production and infrastructure and does not cover further uses and processing of hydrogen. Each of the avenues illustrated in Figure 1 includes guidelines on how to implement key innovations. この表ですね、Direct and Indirect Avenues for Smart Electrification ということで、まずは、スマートエレクトリシティどうなっていくかって、Renewable Electricity ということで、再エネ由来の電気ということで、Direct Electrification は Power to Mobile と Power to Heat and Cooling。やっぱり電動化と電熱。で、あとはそれでエレクトリシティじゃない、Direct Indirect Electrification ってところが、ハイドロジェン、水素っていうところになってくると。で、実際に、この中で、まずはモビルの方ですね。モビルの方でめちゃくちゃいろいろ出てくるんです。例えば EV モデルエボリューション、EV バッテリーサイクリングテクノロジー、diversity and ubiquity of charging points, wireless charging, overhead charging, portable charging station, V2G system, digitalization for energy management and smart charging, blockchain-enabled transaction, smart distribution transfers, smart meters and sub-meters. Dynamic tariffs, smart charging local flexibility provision, smart charging system flexibility provision, light plug regulation, streaming permitting procedures for charge infrastructure, standardization and interoperability, V2Z grid connection code, cross-sectoral cooperation and integrated planning, including EV load in power system planning, grid data transparency, clean highway corridors, operational flexibility in power system to integrate EVs, management of flexibility EV load to integrate VRE, management of flexible EV load to defer grid upgrades, EV as a resident solution, EV aggregators, EV load peak shaving cut using DRs, battery second life, EV charging as a service, EV mobility as a service, ownership and operation of public charging stations, a single vehicle for EV charging at home and on the go, battery swapping. Electrification of mobility status and pace of progress. Adoption of new electric vehicles is accelerating. Under ARENA's 1.5 system scenario, the number of electric passenger cars would grow to 360 million. すごいですね。3億6千万 by 2023 and 2,180 million by 2050. 21億になってことですね。The transition is being boosted by planned ban on the sale of new fossil fuel-powered vehicles, net zero emission targets, climate policies, and other pollution-driven regulations. At the same time, as technological progress and innovation are lowering the cost of EVs, users are releasing the benefits of the technology, such as less noise pollution, better driving experience, and the convenience of charging while parked, and modifying the consumption behavior by making more sustainable decisions. Meanwhile, the rapid growth of EVs poses a challenge for the electricity system. Can it cope with the additional demand? Irene estimates that electricity's share of total final energy consumption in the transport sector will grow to 7% by 2030 and to 52% by 2050. As a result, the global electricity demand from all EVs is expected to reach almost 3,000 terawatt hours by 2040 in Bloomberg economic transition scenario, and 4,050 terawatt hour in the net zero scenario, up from 106 terawatt hour in 2021. And the BNEF scenarios show that about 35% of EV charging will be done at home in 2040. Public fast charging will make up about 24% of the total, with low public chargers and workplace charging comprising another 7% each. Ultra-fast charging for buses and trucks will account for 27% of the electricity demand. All of these will require major investments in charging infrastructure. Under ARENA's 1.5 system scenario, electric charging infrastructure would require a cumulative investment of USD 9 trillion through 2050. BNEF estimates that cumulatively USD 1 to 1.4 trillion will have to be invested in charger hardware, installation, and maintenance. Fast charging from 50 kilowatts to 1 megawatt for passenger and commercial vehicles, which accounted for 70% of all investments in 2022, will drop to around 60% of spending in 2040. Electricity share in transport and EV stock in ARENA 1.5 scenario. ヒストリカル。まず、エレクトリシティシェアっていうところはまず 1% だったものがどんどん 52% に来ますよ。Passenger Electric Cars on the Road。エレクトリックカーっていうのが、実は 10.5 ミリオンということで、まだまだ1000万台ぐらいですかね。っていうところが2050年には21億。みたいなので、ガーンと増えますよっていうのが見てわかります。Growth in charging infrastructure will help to accelerate EV sales by reducing drivers' range anxiety and increasing confidence in EVs. Global EV demand for electricity charging infrastructure and investment ということで、実際にこのエレクトリシティディマンドっていうことで、電気の需要がもうガーンと2040年向けで増えていきますよねと。まだ全然ないですよね。2024、106っていうところが4590と。で、チャージングネットワークっていうところも9から490。で、キュムラティブインベストメントも51から1410ということで、もう画期的に伸びるこの業界っていうのが分かってくると。And Norway's experience with EVs points to the path ahead. Also, the country enjoys some attributes that are by no means universally shared. Norway's progress in electrifying mobility. ノルウェーの国ですね。Norway has made remarkable progress in increasing its shares of EVs, with the share rising almost 86% of cars sold in 2021. By 2021, 16% of all vehicles were electric. The rapid growth has been driven by a large range of incentives, from tax breaks and exemptions to waivers on road tolls and ferry fees. Norway is uniquely positioned to power its EVs with clean electricity. Not only is nearly 98% of the country's electricity generated from renewable sources, chiefly hydropower plants, but the total number of EVs in Norway is small compared with Chinese and the US markets. If all 2.7 million cars in Norway were EVs, they would use only 5 to 6% of the country's annual hydropower output. In addition, hydropower is more flexible than variable renewable like solar and wind, reducing the challenges of charging EVs. For other countries, however, smart electrification also has an important role to play. The importance of smart electrification for decarbonizing mobility. A major challenge to widespread EV adoption is ensuring that the power grid can supply the increased demand with renewable-based electricity. Meeting this challenge requires smart electrification strategies that will increase renewable integration and reduce peak load. やっぱりピークロードを減らすってことも大事ですね。一緒に夕方に立ったらいかんですね。Thus, decreasing grid congestion. Smart electrification also provides important operational benefits for power system through flexibility and storage services. These benefits include reducing greenhouse gas emissions, peak load, and operational costs, and the curtailment of variable renewable generation. A corollary of smart electrification is smart charging to cut the need for additional generation, transmission, and distribution capacity, all in the interest of minimizing invest cost. In uncontrolled or uncoordinated charging, EVs begin charging as soon as they are connected to a charging point. In smart charging, by contrast, intelligent algorithms optimize the charging process, considering electricity prices or renewable generation, local congestion, and battery aging, where electricity prices vary over time. Smart charging allows EV owners to charge when prices are lower. All these benefits increase further when EVs can supply power back to the grid, vehicle to grid, V2V, thus reducing the need for inefficient peaking generators. Figure 1.3 summarizes the results from several studies of the impact of charging options on the power system. Box 1.2 explores these impacts in Belgium and Germany. Impacts of EV smart charging on the energy grid ということで、実際にこのシナリオとアンコントローリングチャージング、スマートチャージングの割合ということで、実際にはアンコントローリングももちろん増えていくんですけども、割合としてはやっぱりスマートチャージングを増やしていかないとピークを削減したりだとかっていうところで大事になってくる。例えば、VRA curtailment with smart charging EV、あるいは reduction in valley、peak difference。やっぱりピークを減らしたりとかでスマートチャージングの割合を増やしていくっていうのはどうしても必要になってくると。At the distribution grid level, smart charging can avoid overloading distribution components and assets, improve voltage quality, and reduce energy losses. These benefits also make it possible to increase the use of distributed energy resources, DERs, without violating network operational constraints. While studies of the operational value of smart charging on the distribution system are difficult to compare. Two common findings are smart charging can noticeably reduce peak load and congestion in the distribution grid. These benefits increase as more EVs are connected and are greater by the electrical smart charging V2G than in the electrical smart charging V1G. Smart charging can reduce voltage drops caused by uncontrolled EV charging, especially at high level of EV penetration. The provision of reactive power from EVs also leads to greater improvements in distribution system voltage. For power system operations, the benefits of smart charging include cost savings of USD 15 to 360 per EV per year, CO2 emission reductions of 0.1 to 2.5 tons per EV per year, peak load reduction of 0.2 to 3 0.3 kilowatt per EV, reduction in the curtailment of variable renewable energy VRE of 23 to 240 kilowatt hour per EV per year. Realizing these benefits will depend on the application of business models capable of extracting the maximum amount of grid flexibility from mobility. Impact of smart charging in Belgium, Germany. In Belgium transmission system operator area performed an in-depth analysis of the impact of electric passenger vehicles on the power system. The study found that smart charging in which algorithms are used to optimize the charging process, considering electricity prices or renewable generation, local congestion, and battery aging, increased the integration of renewables, reduced peak load, and saved drivers money. Smart charging would enable the integration of an additional 1.4 to 1.7 terawatt hour of renewable energy sources by 2030, increasing renewable generation by 30% in Belgium and 37% in Germany. That in turn would reduce the system load that would have to be supplied from non-renewable generation, making it easier to transition towards a fully decarbonized power system. Smart charging can shift charging away from times of peak demand, promoting charging overnight or at times when the supply of renewable energy is high. Unmanaged charging would raise demand by 1.2 gigawatts in Belgium and 6.5 gigawatts in Germany by 2030, whereas smart charging would reduce 2030 peak load by 30% in Germany and 10% in Belgium, as figure 1.5 shows, by shifting charging to times when electricity prices are lower. EV owners can lower their annual electricity cost by 15% when electricity flows only from the grid to their cars, and by 25% when EVs also supply electricity to the grid. And these savings might increase further after 2030 as rising levels of renewable energy increase the spread between high and low prices at different times of the day. Impact of EV smart charging on electricity grids in Belgium and Germany.ということで、まさにこれ面白いですよね。実際な0時から24時までっていうところがある中で、実際に今までどうしても夜が少なくて、実際に昼も少なくて、夕方が多くなってしまうというところを、ここを夜の需要を増やしてあげたり、夕方の需要を下げるっていうことで、実際にこの平準化していくみたいなところを、EV でやっていこうとですね。Blind spots for policymakers. The main barriers to rapidly electrifying transportation are the cost of vehicles and the charging infrastructure they require. As the transaction accelerates, economies of scale and continued innovation will reduce those costs, unlocking investment, boosting sales, and bringing the benefits of clean transportation to more cities and communities. But there are other challenges as well. One is the lack of a clear business model for deploying public charging and ensuring interoperability among charging services. Others are incompatible payment systems, issues of cybersecurity and data protection, and complicated permitting procedures and regulatory measures. Bringing smart electrification to people living in multi-residential buildings can be especially difficult. In addition, policymakers may harbor misconceptions or have blind spots that hinder the development of sound strategies. These are presented in the brief below. Smart charging does not necessarily mean directional charging. V2D, achieving many of the benefits of smart charging, such as peak load reductions, may not require sending electricity back to the grid from vehicles. The implementation of smart charging should thus not be delayed until bidirectional capabilities are included. To accelerate that implementation, it is important to design dedicated smart energy tariffs that reward flexibility and consider EV users as reliable participants in the electricity system. However, whenever possible, barriers to directional charging should be removed because of the additional benefits it can be proved. provide. Development of charging infrastructure should not mimic the petrol filling stations nor are focused only on fast charging. Charging stations should be everywhere. Most charging will happen at night or at work when vehicles are parked for a long time. Even on the go, driver make pauses in their journeys that can be long enough or full charge at normal power, such as during lunch breaks and when traveling with children. Policymakers must keep in mind that the correct paradigm for EVs is to charge when parked, not to park for charging. However, fast charging station will be needed for longer trips, and charging at lower power will take too long. Charging infrastructure should be standardized and interoperable. The current rush to build charging infrastructure has led to incompatible competing systems, creating an unfortunate barrier to EV adoption. It is crucial, therefore, to develop technologies and implement standards to ensure that vehicles, charging systems, and communication networks are interoperable. Planning for EV charging infrastructure development should be inclusive and reflect the local setting. In some countries, most drivers live in multi-dwelling units, and most companies are in multi-tenant buildings. Many do not have off-street parking. Providing convenient and affordable charging in these settings is not only necessary for a fair and just transition, it also avoids a backlash from those who might be left out of charging options. One key policy steps therefore, is light plug regulation, which provides access to convenient and cheap charging. Mobility trends need to be considered in electrification strategies. Mobility patterns are constantly changing, such as the recent growth in remote work and the potential shift from EV ownership to mobility as a service. Planning strategies thus should be tailored for each specific power system and mobility behavior trend. Co-location of EV charging points with solar generation can minimize impact on the grid. Peak solar generation occurs in the middle of the day when most passenger vehicles are parked. Workplace charging combined with solar photovoltaic rooftop arrays and solar canopies um, over parking lots should thus be encouraged. Charging directly from solar arrays also decrease the overall EV load on the grid, and off-grid solar charging systems can accelerate the switch to EVs in places with low capacity grid, avoiding the need for grid expansion. State agencies should coordinate and maintain consistency. Coordination should ensure roles are clear. Regulations on vehicles and grid integration are not duplicated, and the vision for EVs is shared and consistent.